Hello everyone, my name is Yumeka. Today I'm going to present about my research enhancing fault resilience in reinforcement learning-based satellite autonomous task scheduling. So the problem we are looking at is Agile Earth observing satellite scheduling problem. Agile meaning satellite can maneuver along and across track, and Earth observing satellite is satellite with imaging capability. And scheduling problem's objective is to find the best action to maximize the reward for imaging target. And in this research, why we need to consider fault for this reinforcement learning framework. Traditionally, the satellite enters safe mode when fault happen and lose opportunity for imaging. So my research motivation is if the reinforcement learning policy can be resilient for fault. And by handling the fault, then it might not lose opportunity for imaging. So related research is about fault identification, a lot of research going on that, and only some consider post-fault action, but not related to scheduling problem. That's why my research focus is what's new in my research. First, evaluating resilience of curriculum learning policy. I'm going to talk about what curriculum learning is, but by doing that, finding the breaking point of functionality when the reinforcement learning policy doesn't work. And next, making the fault resilience policy by incorporating fault in the training environment. And finally, fault identification is out of scope for my research. So I have strong assumption that fault identification is perfectly done and all the fault information is accurate. With that, let's move on to problem setting. The problem is formulated as POMDP, and state space, action space, reward, and observation space are defined like that. And then reinforcement learning structure is like that, and agent is learn the best action by interacting with the environment, considering the current observation and reward from that. By doing to do that, our lab has developed PSK-RL, which is a combination bus disk, which is a high fidelity modular spacecraft simulation framework, plus Gymnasium, which is generalized reinforcement learning framework. By combining that, this framework is enable us to make the environment for satellite scheduling and tasking and doing reinforcement learning with that. So I'm using this simulation environment for my research. And move on to satellite configuration. This I'm considered a simple example and single satellite with 95 mini circular orbit, and consider 4 reaction coils. With this configuration, reaction coil 1 is aligning across track maneuver, second one is along track maneuver, third one is yaw rotation, and final one is redundant coil, which is important to consider for the fault. And with that configuration, reaction coil 1 and 2 is used more important than the other two for the maneuver for imaging target. So let's move on to fault types. What kind of fault we are looking at? First one is the severe case fault, when the reaction coil is not controllable. It is passively rotate still, but not controllable. And second one is power limit, which lead to limit the control torque for reaction coil. And friction increase is reducing the speed of reaction coil. And finally, measurement fault, encoder measurement turned off or stuck at current value. And all the simulation case I'm doing, fault occurs at the beginning of each episode. So let's move on to training and testing environment. So curriculum learning I talked about earlier, which is based on my colleague's paper below. And curriculum learning is increasing a training difficulty over time during training. By doing that, it is able to run a more robust policy under environmental changes. So in this research, curriculum progression is like that. The battery capacity decreasing over time and external torque is increasing over time during training. And by doing that, creating a very conservative policy to the environmental changes. That's why we think that it might be able to handle the fault as well. That's why we use this as a baseline. And as I said earlier, evaluating this performance by testing different cases, and we observed that gradual performance decrease as the fault severity increase. So now training different types of policies. First one is, as I said earlier, curriculum learning, and the next two is fault and fault LSTM, which doesn't the agent doesn't know what's going any information about fault, but it experiences the fault during training. So the difference between fault and fault LSTM is fault LSTM version use this algorithm, which using the history of observation. I'm going to say the result for those two cases. Without fault observation, there's no improvement in performance without compromising nominal behavior, which we doesn't want. That's why I'm not dive into detail of those two cases, but I'm going to focus on the other three cases. So now, including fault observation, fault bool include the information of if there's fault or not. And the other two cases has the fault information about which reaction wheel has fault. And fault bool and fault num consider the same case as fault and fault LSTM environment. And fault random is a little bit different. Reaction foil uncontrollable fault is a very severe case, but in reality, it's not that severe all the time. And it's more like milder or variety of severity. That's why I include the different type of fault and different severity and randomly pick the value for that. And it is pretty tough to identify what kind of fault happening, but it is easier to identify which reaction coil has fault in reality. So that's why agent only knows which reaction coil has fault. So once all the policy trained, then the testing. For metrics to evaluate policy, first I use normalized real difference, compare the real train with fault and curriculum learning policy, and compute for the same seed. And with this metric, if the value is positive, then this reward is better than curriculum learning. If it's negative, it's worse. So second metric is relative alive rate. So this evaluates the safety aspect of the policy, which is very important, and failure condition is battery run out or reaction foil speed exceeds the maximum limit. And for this one, if the value is over 100%, then it's better than curriculum learning policy, and less than that, then worse than curriculum learning policy. So the other component, the important thing for testing is shield. I implement the shield to all the testing cases to avoid unsafe action. And so first is charging action is triggered when battery drop below the threshold, and desaturation of reaction foil triggered when any reaction foil speed that exceeds the threshold. And with that, I'm moving on to the results. So first, training with fault observation. So I'm comparing the different fault observation cases, and first looking at the reward plot, the x-axis showing the different number of target requests, then solid line showing the case where the agent can observe if there's a fault or not, and dashed line showing if the agent can know which reaction foil has fault. So when the target is 1,000, the curriculum learning policy behave very conservative, but except for that, the Bool one perform worse than curriculum learning policy, but if the agent know reaction foil number, then it perform better overall or comparable result. And if you look at the aliveness plot, then it's very comparable because the scale is pretty small. So we can say that the curriculum, the reaction foil num case perform pretty good. But now the natural question we can ask is that if you know the perfect knowledge of which reaction foil has fault, then why don't we just don't use that faulty reaction foil and shut down it and use the remaining 3 reaction foil? This is testing case for that. And solid line showing this approach with curriculum learning policy, and dashed line is the same as previous slide. And you can easily see that shutting down policy perform much better. So now let's look at the milder fault, not severe fault. For severe fault, it's better to shut down. So why don't we see the milder fault, not too severe case? So let's move on to the fault random policy. As a reminder, it is training in various fault environments as well as nominal, and only which fault reaction foil has fault is observable. So for this presentation, I only show the friction fault result of reaction foil 1 because other cases have similar trend. So if you are interested in other cases, please look at my paper. And with that, the reward plot showing that it's better than curriculum learning cases. But as I said earlier, curriculum learning is very conservative. But I'm more want to look at the aliveness plot, because even you get a lot of points for just 3 orbits, you cannot get any reward after that if you die. And in the real operation, it's not just 3 orbits. So if you look at aliveness plot, then when friction fault is milder, like the multiplier is 10, 100, 200, then the fault random policy perform better. However, the other cases, the severe cases, the curriculum learning perform better. So with that, as a conclusion, I evaluated the fault resilience of the curriculum learning based policy and see the gradual performance decrease with increasing reaction foil fault severity. And for severe fault, shutting down the faulty reaction foil outperform and it's better approach. And for milder fault, training under those conditions with the fault information enhance the policy resilience. However, there's still limitation for this approach. It's overfit to frequent fault, or it is not realistic to include all the fault cases. So it still have limitation, but it's also still show some convincing result as well. So with that, thank you for listening to my presentation. And if you have any question, feel free to reach out to me. And thank you so much.